You're welcome once again. Our previous lesson, we stopped on the derivations of equations of uniformly accelerated linear motion, and we did derive three equations. And we said the three major equations of a uniformly accelerated linear motion. We are to start from here because we agreed when we come back we shall look at the applications of these equations of motion in solving numerical examples. Maybe let us first note something here in the summary of these equations. So we say in summary, comma, the equations of uniformly accelerated linear motion are, the first one we had is V is equal to U plus AT, where V is the final velocity, U is the initial velocity, A is the acceleration of the object, and then T is the time taken. Number two, we had the S is equal to UT plus a half AT squared. Of course, the parameters carry the usual meanings. Here, what we have just added in is S, which actually stands for the displacement of the body. Then the third equation is V squared equals to U squared plus 2AS, implying that now all the terms have almost been put together. That means the first equation of motion relates initial velocity, final velocity, and the time. The second equation of motion relates displacement, initial velocity, acceleration, and the time. Then the third equation of motion relates initial velocity, final velocity, acceleration, and the displacement of the object. Now, for that matter, I think it is now good for us to go and calculate some questions which we apply. In which we apply the equations of uniformly accelerated linear motion. Okay, so let's look at the examples generally. Let's look at the examples. We have examples. Number one, a car accelerated from a velocity of 10 meters per second to 30 meters per second in 4 seconds. Full stop. Calculate the part A, acceleration of the car. Part B, distance moved by the car. Distance moved by the car. Here is always good sometimes to put down the terms that have been given and then get to know what exactly you're supposed to calculate. So in our solution, we are going to first put down what has been given in the equations. In the question. They say the car is accelerated from a velocity of 10 meters per second to 30 meters per second. The velocity with which you start to observe the motion is initial velocity, and the velocity with which you stop to observe the motion is your final velocity. So we are having here our initial velocity. Our initial velocity, which is u, is equal to 10 meters per second. Our final velocity, which is v, is equal to 30 meters per second. The time taken, which is multi, is equal to 4 seconds. If that's the case, then we are requested to get the acceleration. So acceleration, in this case, acceleration A is not known, and of course even displacement S is also not known. In our part A, they wanted us to get acceleration, so I'll say that using, remember, by the aside, you can put these equations of motion that you remember. V is equal to U plus AT. You also have S is equal to UT plus a half AT squared. Then you have V squared is equal to U squared plus 2AS. Now, when you look at that properly, these equations of motion, you can be able to know which equation you're going to use to determine the acceleration of this body. So we are going to say that when you look at this properly, which equation can we use? When you look at the first equation, second equation, and the third equation. Remember, the second equation contains displacement. The third equation also contains displacement. So we can't use these two equations because we don't have the displacement according to the question. That means we now zero our attention to the first equation of motion, where we have the initial velocity, it is known, the final velocity is also known, the time is also known, and therefore we can get acceleration A. So we shall say that using V is equal to U plus AT. So this would mean that we substitute in now the values. When you substitute, you will get 30, which is for V, is equal to U, which is 10 plus A times 4. Now this eventually would mean you have 30 is equivalent to 10 plus 4A. We are going to make 4A the subject of the formula, so that means you have 30 minus 10 is equal to 4A, and eventually this would mean that you have your 4A is equal to 20. So when you divide it throughout by 4, you will come up with the acceleration A is equal to 5 meters per second squared. So that is the acceleration of the car. That's the acceleration of the car. Now in part B, they want you to get the distance moved. So when you look at it properly, we can be able to use the second equation of motion. We can as well use the third equation of motion, because we have already determined the acceleration. So in the second equation of motion, we can use U, which is 10. We have T, which is 4. We have A, which is 5. And we get the displacement or the distance. By the way, this is a scenario where I said that we are going to engage ourselves in calculating distance using the equations of uniformly accelerated motion. Though in deriving them, we are using quantities that are vector in nature. But now at this moment, we want the distance, which would be taken in simple terms as displacement, though they are a little bit differ from each other, because one is a vector quantity, another is a scalar quantity. So here we shall say that using S is equal to ut plus a half at squared, it would simply mean that our displacement S is equal to u, which is already 10 here. It's 10 here, I think you can see it, which is 10 times the t. This t is equivalent to 4 here. So you put this in bracket to be on a safe side. Some students don't know how to treat them when you're multiplying. Then plus a half, this a half here, then times a. The acceleration actually we obtained it here as 5 meters per second squared. You multiply here, then times time squared, which is 4 squared. Now this would mean we have 40 plus in bracket we have a half times 5 times 16. By the way, when you cancel out 2 by 2 here, you would get 1, and by 2 here you would get 8. I think that's clear. So this would mean that your distance is equal to 40, this one here, then plus, remember this is 1 times 5, which is 5, times 8, which is 40, divided by 1, which is still 40, and therefore S is equal to 80 meters. So that is the distance that is moved by the car. Is the proper application of uniformly accelerated equations of uniformly accelerated motion. Let's go to question number 2. Question number 2. Let us visit question number 2. Question number 2. Question number 2, they are telling us that a body starts from rest. A body starts from rest and accelerates uniformly to a velocity of 15 meters per second. 15 meters per second at a rate of 5 meters per second squared. And then the question is calculate the distance moved by the body. The distance moved by the body. Distance moved by the body. So that's what we have as our question. The question is there. So we are to focus on the solution now. Let's look at the solution. We say that the first thing we need to do is to put down what has been given. A body starts from rest. It starts from rest. That means your observation has started when the body is at rest. Your observation of motion is when the body is at rest. So implying this is our initial state. So if that is our initial state, then it means that the initial velocity u is equal to 0 meters per second, because we started observing the body from rest. And they said it accelerates uniformly to a velocity of 15 meters per second. So final velocity, remember when you accelerate, you increase the speed. Final velocity, which is v, is equal to 15 meters per second at a rate of 5 meters per second squared. That means our acceleration which is A, is equal to 5 meters per second squared. Now calculate the distance moved by the body. What we don't have now this time around is the time taken. T is not known, and also displacement or distance moved, which is actually required, that is S, is also not known. But remember, we must remind ourselves about the equations themselves. Besides that, we can have V is equal to U plus AT. You have S is equal to UT plus half AT squared. We also do have V squared is equal to U squared plus 2AS. Now, in accordance to the question, they want the distance moved by the body. And this is exactly what we have that is given. So how can we get the distance moved by the body? Remember, time is not known. If time is not known, we can't use the second equation of motion. Neither can we use the first equation of motion. But we can use the third equation of motion according to what is given, because we know the initial velocity, we know the final velocity, we know the acceleration. So we can get that value. By the way, we can also use the second equation of motion, but only after getting the time taken. How? I will give you that as an alternative. Let us look at how we solve using the third equation of motion. So you are going to make a quotation here and tell the examiner that using V squared is equal to U squared plus 2AS. This would mean, what is V? 15 square root is equal to U squared, which is 0 squared. Then plus 2AS is 2 times 5 times S. Alright, and then when you look at it properly, this is 225. I think I'm right. I'm right to say 225. Maybe. Yes, 225. Is it correct? Yeah, someone is telling me it's correct. Is equal to 0 plus 2 times this is 10. So 10 seconds. I mean 10s, not seconds. So it means 10s is equal to 225. I have not changed anything, by the way. Still equal. It's still an equation. This can be on the left, this one can be on the right. Even if I use the simple mathematics that if this one crosses goes to the left, it becomes negative, and then this crosses goes to the right, it becomes negative. I divide throughout by -1, I still come back to this. This is S, not 5 members. This is S. So I divide throughout by 10. I divide throughout by 10. And eventually, I have my distance moved. My distance, S, is equivalent to 22.5 meters. The SI unit is meters. The SI unit is meters. So don't get confused there, and again use meters per second squared. No, meters per second squared is for velocity, and then meters is for distance or displacement. From the first part of linear motion, we did give the units of all these common terms used, and for distance we gave it as meters. Okay, I promised to give you the alternative way. So alternatively, what do we have here? Alternatively, you can say that using S is equal to UT plus a half AT squared. But T, you remember from the first equation of motion, we said T is equal to V minus U divided by A. So this means that UT is going to be V is 15 minus U, which is 0, divided by A, which is 5. All those terms, by the way, are up here. You see U is there, V is there, and then A is there. So that becomes 15 divided by 5, which gives you 3 meters. Sorry, this is 3 seconds. Oh, 3 seconds. 3 seconds. By the way, don't take this to be rough work. No. this is part of this calculation because you need the time. So we said but, so it is part of the calculation and you're going to get marks for this. If you put it somewhere else and then you just substitute, you will not get the mark. We shall assume you copied from somebody, and that is not good. We are trying to test and find out whether you know what you are actually calculating. So if you want us to know that you really know, so you must put the rest of the working on your answer sheet, just like the way I've put it there. So this actually would mean that your distance is equal to u, which is 0, times t, which is 3, then plus a half times a, which is 5, times t squared, which is 3 squared. And this would mean that we have 0 plus a half times 5 times 9. Remember, 3 squared is 9. So this would imply furthermore that s is equal to this 0 just can be left out, and then when you divide this 2 by 5, you actually get 2.5. So we shall have 2.5 times 9, and eventually our distance becomes 22.5 meters. So that's how we can calculate the distance using the first method and then an alternative method. Of course, the alternative method is long. That is if you involve yourself in getting the time taken. Okay. Now, for that matter, we are going to give you at least a question. We are going to leave you with a question. You also try to do this question and get the answer on your own. Try your question. What does it say? A body moving with a velocity of 20 meters per second accelerates uniformly to a velocity of 30 meters per second in 5 seconds. Full stop. Calculate the part A, acceleration of the body. Acceleration of the body. Then part B, distance moved by the body. Distance moved by the body. Sometimes students always want to be given a hint. I'm not going to give you the hint, but I'm going to leave you with the answers to these questions, such that when you're calculating, you can easily know whether you've got it correctly or you haven't got it correctly. But I think I need to give you 2 questions. Let this one be question number 1. I give you another question also. This one, the acceleration is 2 meters per second squared. Then this one, the distance s is 125 meters. Yes. Let me give you question number 2. Such that you also see a different version. Can say different version of question. It says a car moving within a velocity of 25 meters per second retards at a rate of 2.5 meters per second squared, full stop. So the question is calculate the part A velocity of the car after 8 seconds. Part B, time it takes to come to rest. Then part C, distance moved by the car. I think I also need to give you the solution to this question, but I think you also need a hint here. Maybe there's a need for a hint here. For example, part A, the solution here is V equals to 5 meters per second. Part B, the solution here is time taken here is equal to 10 seconds. Then part C, the solution here is S is equal to 125 meters. By the way, the hint I'm going to give is how we are going to calculate. Remember, we are going to use the equations of uniformly accelerated motion. V is equal to U plus AT. You will use S is equal to UT plus a half AT squared. You will probably use V squared is equal to U squared plus 2AS. Now, in all the equations, you've got acceleration involved. In all the equations, there is acceleration involved. I want to pull it out and you see. There is this acceleration here. I think you can see it. There is another acceleration here. There is one here. All of them are involved. Now, what they gave you is not acceleration. They gave you what you call retardation or deceleration. Retardation was given to you as 2.5 meters per second squared. In this case, acceleration will be negative of 2.5 meters per second squared, because remember we said retardation is negative acceleration. Therefore, acceleration is also negative retardation. When you are substituting the value of acceleration, you will not use it as 2.5 meters per second. No, but you will use it as negative 2.5 meters per second because it is retarding. So watch out. The first question, they wanted the final velocity after 80 seconds. So get to know that time in that case is 8. You know the equation you're supposed to use. You will check out of the 3 which one is suitable for that question. Then part B, the time it takes to come to rest, implying that this time around the final velocity I'm giving a hint, of course, is 0. Initial velocity will have been the other velocity it was moving with. Then you know how you will get the acceleration. You know the acceleration you substitute. Then distance moved by the car. The distance moved by the car, of course, in the entire journey until it comes to rest. That's what they mean. So for today, let us stop on this particular example. Probably when we come back, we shall remind ourselves on the examples that are related to this before we go to another part. Thank you so much for your cooperation today. Bye bye. We meet next time.